Defects in steel plates can affect the strength and also ability to use that steel plate in certain applications. Even the manufacturer of using that plate in different applications, it might affect that with the defects. So we want to be able to detect the defects, and we're going to use this sample data set. Image analysis has revealed 27 different features to describe a steel fault. And there are 7 different types of faults. So let's say there's some different type of fault on each of these plates. We have taken a picture, or the person that generated these took a picture of these and came up with feature 1 all the way through feature 27. And then as a result, they describe the defects that are in them. And the defects were strings that are listed 1 through 7, okay? And then these are encoded with one-hot encoding. So defect 0 all the way through defect 6, those would be a 1 if it's present, okay? And then 0 if it's not. And so for each of the defects, there's going to be either a 1 or a 0 to share which one is present. So one of the challenges with this is now we have all of these categories of defects, and we have this multiple output that we have to deal with in doing the classification. So this is what the confusion matrix is going to look like in the end. We want high numbers along the diagonal, meaning that our predicted versus our actual. Okay, so this is our actual, that we have good agreement between those. But if it's, the actual is, for example, this type of defect that we predicted the first one, or 0 in the index, then we can see that's a misclassification. We also have a lot of misclassifications here. So we want to try to minimize those in doing this classification. We want to try to predict the correct type of defect from those 27 features. Now, as you can imagine, some of those features are going to be more important or less important than others. So through this exercise, we're also going to quantify which ones are most important, because it takes a while to create all the features from the images, and so it can reduce maybe when you take a photo, the type of data that you have to collect to be able to analyze whether it's the type of defect it is. So let's go through this exercise. Here is the link that I'll put in the video. And you can see also the data set that's available. Here are the 27 different features. And then you can also see the 7 different faults. And those are going to be a 0 or a 1 for each one. All right. But in this case, you don't have to download that. You can just import it with pandas. And we're going to go through these notebooks here. You can either go to Google Colab and open it up here, run it through your web browser, and it's also available here with GitHub. Just come here to the raw, right click, and go save link as. You can save your Jupyter Notebook to your local hard drive. So I'm going to use, in this case, I'll use VS Code. And let's go ahead and just first load in some packages like pandas, matplotlib, Seaborn, and then some scikit-learn packages, sklearn for short. We'll load in confusion matrix, a min-max scaler, a train test split, and select k-best. That's going to be used to determine which features are most important. And then some keras packages as well. We'll have a sequential model and then also a dense model. Okay, so that one ran. It's currently has some errors here. It says these are not used, and then those will return to a different color as we use those. Okay, so here's the pandas, data frame will have data, read CSV. We're going to read this steel plate, and there's our sample. So as I run this, I'll see that it read in this data frame of values, and there you can see, the defects that are here, 0 or 1 for each one. So I just took a sampling of those, a sample of 10 of those. Actually, I think I just changed color schemes on this, so maybe it is going to stay red for some reason on there. Okay, so let's keep going. We're going to detect some outliers now and remove bad data if it's present in here. So we'll get our features are going to be these last 7 columns of our data, and we'll just say that data features, and we'll plot that, and we'll plot it with a box plot and say that subplots is true, so that we create a separate plot for each feature. And then let's create a layout. Because we have 27, let's make 30 of them, 5 by 6, and then make it the figure size just a little bit bigger, and then we'll show the plot. And so let's go ahead and just run this, and here are all of the features, as you can see from the box plot. We might want to eliminate some of these that have, for example, a big outlier here, eliminate some of those values that might be skewing the results. Okay, so in this case, we would want to detect and remove if present. So one of the things that we can do is now generate some filters on this. So I'll go ahead and just insert a code cell below, and let's go ahead and just separate out some of them, like let's come over here, pixels, areas. Okay, and there's one that's just very high there, and maybe we'll just go ahead and just create a box plot just with that one. Okay, and so let's just go ahead and do pixels, areas, and we'll do plot with kind equals, and then create a box plot. Okay, I keep hitting Control Enter. I'm used to, okay, let me get the right name, pixels, areas. Okay, I got to make sure I have the right feature name. That might be an underscore there. I keep hitting Control Enter. Okay, so there it is. It was an underscore there. And so you can see that this is way outside the limit just for that one there. So let's go ahead and just filter this out. We'll just say that data equals, and then I just want the data where data pixels areas is going to be less than, and let's say 60,000 there. And I hit Control Enter again. It's just the muscle memory. Okay, so I've eliminated that bad one there. So you can go through and eliminate other ones as well. If you generate that, let's just generate that plot again. We'll just do data and then pixels, areas. Getting used to the Copilot. Let's giving suggestions. Okay, and run this one. Okay, so I've eliminated that one large outlier, and you can go through and just eliminate those. Do it based on standard deviation away from a mean or something like that. Okay, let's go ahead and just show the balance of the labels as well. I'll say features again. That's just the last 7, and then we'll say our labels are the last 7. Okay, so features up until the last 7, and then labels last 7. And then we'll say X is going to be our data for the features, Y is going to be the data with the labels, and then let's just go ahead and take the ID. So this is going to be the column name of the maximum value in that row for axis equals 1. And we'll just do a values count. And then let's create a plot of that. And we'll do a bar chart with figure size 12 by 5. So this just shows other faults is the most. You have bumps, K-scratch, Z-scratch, pastry stains, dirtiness. So anyway, you have these different faults. I don't know what pastry is. Maybe they spilled a donut on the plate or something, or on the steel plate or something. I'm not sure. Okay, so you have different faults. You can see that stains and dirtiness, those are the lowest. And this is a very imbalanced data set that you might have to fix by oversampling the minority classes or undersampling the majority classes. There's just additional information on that here on the course website under imbalanced data. And so if you'd like to do that to improve this, you'd likely get an improvement by balancing the data. So there's just some examples here on how to balance the data. I encourage you to do that if you'd like to further improve this solution. Okay, so that's the distribution of how many are in each one. And now we want to scale, select features, and split into a train and test data set. So I'll go ahead and scale the data. Let's use a min-max scaler, and we'll have our data scaled is going to be with our fit transform. We're going to fit the data, and then we're going to convert that back into a data frame and use the same columns that we had before. So in this case, it's a min-max scaler. So we can also do this to the labels because they're 0 or 1, so they'll still remain 0 or 1. But you normally don't scale the labels, especially with classification where those need to be integer values. So let's just split the data into X and Y. We have features, so we'll take our up until the last 7 for our features, and then our last 7 for the labels. And we'll again define X and Y. So splitting those out from the scale data. And then we'll also do the train test split. We'll have our X train, X test, Y train, and Y test. And we'll use a train test split with X, Y, and then we'll have our test size. We'll shuffle. And let's run this one. So now we've scaled our data. We've separated it out into the features and the labels, and then we've split it 80-20. So 80% for the training, 20% for the test. Now let's get our select best features for the classification. So our best features, we're going to use select k best. We'll use a chi-squared for the score function, and we'll just include all with our best features just so we can look at them. We'll fit our best features with X and Y, and then create a figure with these, with the scores. So I'll create a bar chart with our X columns, and then our height is going to be the score. And then we'll just rotate the X tick so that it's going to be up and down. They won't cross over. Okay, so we have a few types of features. Our type of steel, if it's A300 or A400, those are the most important for the types of defects. So it's possible that, for classifying these, certain types of steel are more subject to, have a certain type of defect or another. And the sigmoid of the areas, that's high. You also have the sum of luminosity, the Y perimeter, X perimeter. So maybe the size of the defect, the pixels area is also important, and X min, X maximum. You can see a lot of them, like the Y minimum, Y maximum, those are very low. And so We also have others like the maximum of luminosity or the empty index or others, luminosity index. So these are likely features that we could remove from the classification problem, or not use those, include those in the image analysis to extract those, because they're not very high on this ranking of important features. Okay, so all right, so there is our plot. Now let's go ahead and create a one-layer neural network in Keras. So this is classification neural network with Keras, and let's create a model. It's going to be a sequential model, and I'll add a dense network, dense nodes to it with 8 of them, and I'll have our input dimension be this input. So these are the 27 features here. These are the number of columns that we have. So the shape 1, and then I'll use an activation function, a rectified linear unit. And then also add another dense layer. This is going to be a softmax coming out. And so we're going to get some probabilities. And then we'll compile it. We'll have a categorical cross entropy. We'll have our optimizer be atom optimizer. Metrics will be accuracy. And then let's go ahead and train the model now, where our result will be as a result of the model.fit. So we're going to use the fit method with our xtrain and ytrain. And then this is the number of iterations that we're going to have to update the parameters, epochs, and then we'll have the validation split. And we'll say verbose equals 0. So this is going to train. So if you had verbose equals 1, you would see some of the output from this. And actually that's actually helpful to see. You can see as it's training, how the accuracy is doing. But let's go ahead and just continue on. We'll create a plot, the train and validation functions. We'll have a semi-log y plot. Okay, and we're going to have the loss function and the validation loss function. So this is on our test set here. This is on our train set, and so it finished. And we'll create a loss and then a validation loss. We'll put a legend, a y label, and an x label. So let's just see how this did as it trained. You can see, the validation that on the test set, it did not increase, so we weren't overtraining necessarily. We can see this decrease. This is on a semi-log y plot, so we can see both of them are decreasing even up through 1,000 iterations here. Okay, so no evidence of overfitting. Maybe a good fit, we could say, if we don't need as many, maybe somewhere down here around 500, it starts to really level out. So not as much benefit after you reach that point. All right, so let's create the predicted labels and probabilities of those labels. And we're going to save those in a data frame. We'll also highlight those as well. So let's go ahead and predict what the outcome would be, what the defects are going to be based on this X test data. And we'll convert that back to a data frame with our Y test columns. And then let's extract the labels and the probabilities as well. So we'll have our predicted label is going to be, again, we're going to take the column name of the maximum value in each row with IDX max. And so there's our row indicator axis equals 1. And the predicted probability is going to be the maximum along that row. So we're going to get the probabilities from it because we gave it a softmax output. And then our actual label is going to be Y test. We'll take the label of the maximum along there. Nice, that's going to be a 0 or 1. So we'll just find the one that has the 1 and show what label that is. Okay, so now let's display those probabilities and which faults are most likely in the actual. Okay, so we'll have our actual fault. This is going to be that actual label, and we'll just take the values. And then let's highlight the max. So this is our table of values. This one's going to be quite long, but it just shows the the actual fault. It's pastry. You see that was the highest probability. You see the bumps. Okay, and then we have K. I'm not sure if that's supposed to be K scratch or K scatch, but anyway, that's 96. There's a 68, so not as high there, but it's higher than any of the other ones. There's 93, 75. Now this one, for example, it isn't very convincing. Which one it should be. We also had this one, which was about 15%. This one was selected because it was 42. But this other faults, it could be 39. So it really wasn't sure which one it was, but it selected that one as the most probable. So this one gives us some indication of the probabilities. This one as well, other faults, it was selected bumps, but other faults was also quite high as well. So you can see how well it did, but this is these are a lot of numbers here, and going through it would be hard to really make sense of how well it's doing. So let's generate a confusion matrix instead. So we'll generate a confusion matrix from the predicted label and the actual label, and we'll use those are still going to be numbers, so let's turn it into a heat map, and we can save that locally and then also show it. Okay, so here's the heat map that we had generated from before. These are slightly different. Sometimes the neural network is going to start with different initialized values. Maybe we filtered out some of the outliers a little bit better. So each one's going to be a little bit different depending on how you prepare your data. But this is got high numbers here along the diagonal. You can see that even though this one had a minority of samples, it still did fairly well in predicting that. So if that was not predicted well, you might have to do some oversampling of this or undersampling of some of the higher, more highly represented faults. Okay, so let's get the score and accuracy as well. We'll evaluate score 1, accuracy 1, score 2, accuracy 2. We'll evaluate the X train, Y train, and the X test, Y test. All right, and so there is our loss, okay, and then the accuracy, and we've just stored those here, the score and accuracy. Okay, these you can see 72%, 64% for those two. Okay, so let's look at the sklearn classifiers as well. We'll just compare this, the Keras TensorFlow, to how you can also do this with sklearn and some additional unsupervised learning methods. If you'd like to come here to this classification overview, it'll show you some additional links. So on each one, it'll show you some of the background. We'll have a logistic regression, for example, how it's calculated. It gives a lot more information on each method. But let's just use sklearn. We're going to import these packages, these 8 classifiers, and I'll just go ahead and run that. And then the other thing that we need to do is, because these are not set up to have multiple outputs or multiple labels, and so we're going to have to also import the multi-output classifier. Okay, let's import that one as well. The packages here are not showing up too well. Let me just go to preferences and let's see, color theme, and let's maybe go back to a Visual Studio Dark. Okay, that looks a little bit better. The red was kind of bothering me there. Okay, so let's run this one as well, and then let's create some models. Here's the different 8. Okay, we're going to create those and create these objects. Okay, I'm going to also create the classifier list, and I'll just put those 8 into a list. The next thing that we're going to need to do is also create an M list. So these are going to be our model lists, because we're going to use this multi-output classifier. So I'll just initialize this with none times 8. I'll just leave 8 blank values in there. All right, let's go ahead and train the models now. So for I, comma model in enumerate, and then we're going to take that C list. We're going to take this list of 8 right here and cycle through those. And we're going to create this new list, this multi-output model list. And so we'll use a multi-output classifier, and we'll do M. Okay, so it's going to take that object, and then it's going to train one for every one of the outputs, and then take the highest probability for each one. Okay, so there's our X train and Y train. And let's go ahead and just train all 8 of these. You'll notice that Keras TensorFlow, that one took a little while. This is training 8 of them, and it'll actually probably compute just even a little bit faster. There might be some warnings here if the number of iterations isn't high enough, for example. Maybe I set that too high for the max iterations for the neural network. We'll see how long this one takes. Okay, but while that's going, let's go ahead and just get some train and test scores. Okay, so we'll create a new data frame. We'll initialize this. Let's compare it to the Keras TensorFlow neural network. We'll get the score for the training and the score for the testing. And then let's go through this list again, like we did before. In this case, we're going to enumerate the M list. And we'll say that, let's get the name of the estimator, and then append the score for the training, and also append the score for the testing in S1 and S2. So there it's going to score all the model performances, and then we'll create a bar chart with both the train and the test. Make the test just a little bit less wide, 0.5 instead of 1, so it doesn't cover up the train all the way. And then we'll rotate the exact labels and show. So this shows the performance of each of those classifiers. So decision tree classifier was perfect, random forest was perfect, but you could see they had a little bit lower test performance than some of the others. So the highest one was, on the test at least, was the Keras TensorFlow neural network. And then up there was, maybe the neural network classifier. This was max iterations 10,000. So that was close. It did really well on the train. Some of the other ones that performed well are K nearest neighbors, decision tree, random forest, but you can see that there's a big difference between what they did on the training versus what they did on the test set. Now the worst one was down here, the Gaussian naive Bayes, and that's interesting because it got about 20% right. Even if it's just guessing, you'd expect it might do like 1 out of 6. Okay, so that's about 1 out of 5 with 20%. So not much better than just guessing. And these are also fairly low, for detecting the right type of fault. But maybe the probabilities show some kind of like an indication about when it's certain about those versus when it's uncertain. If it's uncertain, maybe you wouldn't trust that, or maybe you'd have to go and inspect that yourself. Okay, so that's the code for this. The example notebook, it has all of this code already in there, so you can just run them. It's more like an example notebook that you can use just to see some of the methods to train a neural network with Keras and TensorFlow, and then also compare that with sklearn. So let's just come back to the course website and just show where this fits into, we have the schedule here. If you'd like to go through this, we included this with steel plates faults here with the regression topics. And so this is more of a learning exercise along with the others. And then the assignment is k-nearest neighbors and polymer melt flow rate.